Welcome back, everyone. In this video, I will be going over the lecture for implicit differentiation. Now, in this section, we'll talk about what implicit differentiation is. Kind of realize that we've been doing it a little bit, not completely, but we really have been doing the idea of implicit differentiation every time we do a derivative. Then we're going to look at the remaining derivative rules that we have not yet used because they require knowing how to do implicit differentiation, and those are the inverse trig functions and the natural log y equals the ln of x function. After that, we'll just practice our new rules, either the implicit differentiation technique or just our new rules, the inverse trig and the natural log derivatives. And then at this point, we'll pretty much have all of the derivative rules, derivative techniques covered. And there's only going to be a couple minor ones after this. But after this section, if you're comfortable with all the derivative rules, you can really do all the derivatives we've done through the chain rule and this section. You're in a really good spot for being ready to do any derivative. All right, but I want to go ahead and start off with what is implicit differentiation? What is the idea behind it? Well, the idea starts off very basic, for a lack of a better term. You do the derivative of each side of an equation. And what I always like to show is that you've been doing this the whole time. Okay, so if you had to do the derivative of y equals e to the x plus x squared, we don't usually write necessarily d over dx of the left side of y, but we're actually doing it every time because when we do the derivative dy over dx, or d over dx of y, this is just what we call dy over dx. And that's exactly what it is. Oops, and I just wrote the dy on the bottom by mistake. So dy over dx is exactly this. Basically, when we do the derivative of y, we don't have a rule for y when we're taking the derivative with respect to x, so we just call it dy over dx. But that's exactly what we always want to figure out. Dy over dx, sometimes we use y prime, sometimes we have a name for a function like f of x and we use f prime of x. But ultimately, we're doing the derivative of every side, and if we wanted to complete the derivative, we know we would do the derivative this side and apply all the rules in our knowledge from before to do it. All right, so why can this one be done so easily, quote unquote? Well, the reason you can do this one directly, you just get dy over dx when you do the derivative of each side, is because you have y solved for. It's y equals something. When you don't have y equals something, it's not always possible to make it y equals something. There's plenty of examples, and probably the easiest is a circle. So any graph, if you were tried to graph this, it would pass the vertical line test because it's y equals stuff with just x. But a circle, we know just from knowledge, a circle is not going to pass the vertical line test. And the equation of, let's say, the unit circle, the circle with center of 0 and radius of 1, is x squared plus y squared equals 1. Because this will fail the vertical line test, you have to use implicit differentiation. It's just required. If you cannot make it y equals, then you have to use implicit differentiation. Now, maybe you're thinking, I can make that y equals. You can, but you're going to get two equations. So I'm not going to go through the details, but if you try to solve for y, you'd subtract the x squared, and then you'd do the square root. You'd get y equals the square root of 1 minus x squared. But when you do the square root, you have plus or minus. And this is because one of the square root, you do plus or minus, but also when you draw a vertical line, it passes up to 2 points, which means you're going to have two equations. One for the top half of the circle, one for the bottom half. And to do the derivative of this, you would have to do the derivative of each one of these, so two separate derivatives, and then sort of combine them in a way to make it easy to plug in numbers and know what you're talking about. But with implicit differentiation, we can just do the derivative right away of each side, solve for the derivative, what we're trying to solve for, and then go on with our lives. All right, so the main thing is going to be in this section is really the notation that we've been using all since we started doing derivatives. When you do the derivative with respect to a certain variable, this means all other variables need to have the chain rule applied to them. So what I mean is, to start off, when we write d over dx of something, whatever this something is, it can be anything at all. We want to do the derivative with respect to x. Okay. And we've seen examples of this because that's pretty much all we've done. We've changed up the letter. Of course, we could use any letter to the derivative with respect of, but the emphasis here is that if we wanted to do the derivative with respect to x of x cubed, we have a power rule that tells us we can do this, but we can do it with the power rule only because we're doing the derivative with respect to x, the same format. So if I had a different letter, let's say I wanted to do the derivative with respect to t, but I had t cubed, well then I can still do the same power rule because I still have t. And you could just write down the answer to these if you want. We know this would be 3x squared, this would be 3t squared, just the difference of letters here. But the point is, the thing that's being cubed is exactly the variable we're taking the derivative with respect to. Now, when we introduced the chain rule last section, we talked about how to do the derivative if the thing you're raising to the third power, just to stay with this example, is not just x. So the other one I have written here is that we have x, do the derivative with respect to x. So we're still trying to do the same derivative, but the thing being raised to third power is not just x anymore. It's 3x plus 1. They don't match, which means we need the chain rule. Okay. And the main point of the chain rule was that we pretty much follow the format of the power rule. In this case, we started off, we bring the 3 down, we rewrite what's inside, the 3x plus 1, and then we subtract 1 from the power, which is 2. But the chain rule part, this is going to be the most important thing about this section, is when you do implicit differentiation, you're pretty much always going to use the chain rule, and you're multiplying by the derivative of the inside. Now, I'm not going to actually write down what the derivative of this is. We know it's 3, but I'm just going to write down the formula. D over dx of 3x plus 1. Right? So that would be exactly what the chain rule says. Because these do not match, we have to multiply by the derivative of the inside. Otherwise, it looks a lot like our power rule. Well, now in this section, instead of having just something inside that has x in it, but it's not just x, we're going to have completely different letters. What if I had y instead of x? So what if I wanted to do the derivative with respect to x, but I wanted to do the derivative with respect to x of y cubed? Well, the first thing is that because these aren't matching, the derivative we want to take with respect to is the letter x, but our variable inside is y. They still do not match. Do not match. Well, for the same reason as above, I have to use the chain rule because they do not match. It doesn't matter what's inside here. If it's not just x, as far as our variable, it could be 3x plus 1, something with x, or just a completely different variable. They don't match. We must use the chain rule. And in order to use the chain rule, we follow the same format up here. So what I'm going to be doing is basically the same exact setup. Imagine if 3x plus 1 was y. What would we have here? Well, it's exactly what I'm going to write here. We would still do the power rule, start off with the power rule portion. We bring the 3 down, rewrite the inside, which is y, and then subtract 1 from the power. Now, this might be the natural step where if I wasn't pointing all this out, you would stop. The derivative with respect to x of y cubed is 3y squared. But because they don't match, we must use the chain rule. And the derivative of our variable here is the y, the quote unquote inside when we talked about the chain rule last time. In this example above, the inside is 3x plus 1. Well, in this example, the inside, the thing being raised to the third power is y. So the inside, we multiply by the derivative of the inside, that's our chain rule, d over dx of y. And now what is d over dx of y? Well, that's just dy over dx. That's actually the exact name we give it. We don't have a better name for it because we don't have a rule for what is the derivative of y. It's just the derivative of y. So sometimes we write this dy over dx, sometimes we write it y prime. You can write both. The one thing I would refrain from doing is writing it as like f prime of x, because we're not giving this a name, it's just y. So either dy over dx is the way I would think about this derivative, or equivalently, if you prefer y prime, 3y squared times y prime. Now, the reason I would suggest trying to use dy over dx instead of y prime is that dy over dx tells you the variable you're taking the derivative with respect to. Of course, if you have x's and y's in your equation, then y prime just automatically means the derivative with respect to x, but it's clearly more labeled if you write dy over dx. So I pretty much only use dy over dx and not y prime. That's another reason why I tend to use dy over dx over y prime, even though y prime is easier to write. All right, so the main thing I wanted to introduce here at the beginning was the idea of what we're going to be doing, because I didn't want us to go through problems and come across like a y cubed in a problem and write 3y squared times y prime and then have to re-explain all this. So just keep in mind, whatever letter you're taking the derivative with respect to, it doesn't matter what it is. When you think about doing the derivative, if the inside of whatever it is doesn't match exactly, so it can be a different format with x, it can be a completely different letter with y, you have to do the chain rule. And general rule of thumb, usually we use y's and x's, but we can definitely switch up the letters. We can use t instead of x, we can use z or w instead of y, and just a whole bunch of different combinations. That's why it's very important to write this d over dt, d over dx, whichever one you're doing, and make it easier on yourself to read. All right, now before we tackle specific examples with implicit differentiation, I wanted to show you how to get the derivative of the inverse trig functions and the natural log function. Now there's there is 6 inverse trig functions. For the most part, you only deal with 3, which would be inverse sine, cosine, and tangent. The other 3 aren't used as often, but you could figure them out if you want. And what I'm going to do in this section is show you how to get the derivative of the natural log of x and then also the arc cosine of x, or cosine inverse of x. All right, so I'm going to start with compute dy over dx if y equals the natural log of x. And this example, even though the formula is short, is going to be much harder than the examples when we do implicit differentiation, because we have to do a lot of manipulation and plugging back in things that we're not going to have to really do when we do our own implicit differentiation. But in this problem, I'm giving you the formula for this derivative. All right, so what do you have to do here? Well, I'll start by writing y equals ln of x. But one thing that is vastly different from this example is that if we just did the derivative of each side, which it really is what implicit differentiation means to do, on this side we would get dy over dx. On this side we would be asked to find the derivative of the natural log of x, but we don't have a formula for that. So you can use your log and exponent rules to switch this to exponential form and then do the derivative. And if you're not familiar with that, the easiest way to remember that, you should have all seen it before, but the natural log has an invisible base e. It's like log base e. Typically with ln, we never write base e because it's just written there, but it's also repetitive. But you grab your base and bring it to the other side, and it becomes the base of the exponent, and you get the equation e to the y equals x. Now this is more along the lines of something we would do the derivative of using implicit differentiation. Why? Well, because we don't have just y equals anymore. We have e to the y equals. But at this step, we have to use implicit differentiation because it's not y equals. But at this point, we're going to use the derivative, do the derivative, so that requires implicit differentiation. And I'll just write a little comment since it's not y equals. Once again, just to reiterate, I'm showing you how to get the formula for y equals ln of x. At the end, when we get that formula, you're just going to be one of those formulas like the other derivative rules you just want to memorize. All right, so we've got this. Now we do the derivative of each side. So we do dy, sorry, not dy, just d over dx, already jumping ahead of myself, of the left side, e to the y, equals d over dx of just x. All right, now the right side is really, really easy because this is our normal standard rule, pretty much the first rule we learned about derivatives. If the inside completely matches the derivative or variable we're taking with respect to, which is x, it's just 1. So x and x, it's just 1. What about the left side? That's definitely the more complicated side. Well, the best thing to do is how I described it before. You almost pretty much, when you see a y, you do the rule. What is the derivative of e to the x? It's itself. So when we start the derivative of e to the y, it's itself. But then we multiply by the derivative of the inside. And remember, the inside for an exponential function is the exponent. So this was the first part. And then we multiply by the derivative with respect to x of the exponent, which is y. And now dy over dx, or d over dx of y, is what we call dy over dx. So I'm just going to write dy over dx. And this equals 1 because we haven't done anything there. And now the point with implicit differentiation is you solve for dy over dx, because that's what we want to do. We want to compute dy over dx. And to do that, we could divide each side by e to the y. I'm going to go ahead and do that. So this is one thing that's new, is that at least as at this point, when we get dy over dx, we don't necessarily have just x on the left side or right side anymore. We can have y's as well. We get dy over dx equals 1 over e to the y. Now, in a lot of examples with implicit differentiation, once you get here, you're done. Once you get dy over dx to here, you're done. But we can actually, just because this is the special natural log rule, we can actually go further, because e to the y actually equals x. And if we plug that in, e to the y equals x here, we get dy over dx equals 1 over x. And that's actually the rule for the natural log of x. So just to recap, we started with y equals the natural log of x, and we just discovered that if you do its derivative, it's 1 over x. All right, so let me go ahead and highlight this new derivative rule. It's the derivative with respect to x of the natural log of x equals 1 over x. It's kind of crazy how simple looking the derivative of the natural log is. Now, because we've learned the chain rule, when you do derivatives of natural log, you don't have to have just x inside, and we'll see an example later dealing with that. But kind of record this, write this down, because this is the main thing you want to take. I just wanted to show you that it uses implicit differentiation to actually get it. All right, so even though this video is approaching 20 minutes, I do want to go ahead and just do arc cosine as well, and really have the basis so we can move on to the main point of this section. All right, so we want to go ahead and now I'm going to do arc cosine. You could do arc sine, you could do arc tan, arc cotangent, arc cosecant, arc secant. Although those last three aren't very often used, but you can do them all with the same idea here. So it says compute dy over df if y equals arc cosine of x. And just a reminder, if you're not familiar with it, or you just don't remember it, arc cosine of x is the same thing as cosine inverse of x. It's just almost always better to write arc cosine instead of cosine inverse, because you don't want to get confused and think that this is an exponent, because it's not. Kind of the strange thing about trig functions is we usually write the exponent here. So if you have cosine squared, it would be, the 2 would be right here. But if you're talking about the inverse, the -1 does not mean an exponent. So I like to use arc cosine or arc whatever. All right. So the idea is going to be pretty much exactly the same. I'm going to rewrite the equation. And I'm going to have to convert this one first, because I don't know the formula for the derivative of arc cosine of x, which means if I go ahead and just do the derivative of each side right now, then I can't simplify this side. Well, the thing you want to remember about inverse trig functions is that you can move them to the other side as their regular counterpart. So arc cosine of x over here becomes cosine of y, and you get cosine of y equals x. So hopefully you remember that. The main reason is that you do the cosine of each side, and when you do the cosine of each side, the arc cosine and the cosine cancel out, so you get cosine of y equals x. But once you're here, this is sort of like after we switched to exponential form last time, we're right here. Now we want to go ahead and do the derivative of each side. All right, do implicit differentiation. Because we don't have y by itself anymore, but we know how to do the derivatives of cosine function and just x. So that's why we can do the derivative of each part. We do d over dx of cosine of y equals d over dx of x. And go ahead and once again, the right side is just 1. The d over dx of x is 1. Now, what's the derivative of cosine? That's negative sine. We get negative sine of the inside, which is y. But because y doesn't match x, the derivative we're taking the variable with respect to, we have to multiply by the derivative of y, which is dy over dx, our chain rule part. And if you want to write y prime instead of dy over dx, you can, but I'm just going to do dy over dx. All right, now just like last time, you can solve for dy over dx, and you want to anyway, because that's what we want. We divide each side by negative sine of y. And when you do that, we have dy over dx equals 1 over sine of y. For the negative sign, you can put it anywhere. I just like to put negatives either on the top or in the front. I don't like them on the bottom. All right. Now we want to do the same sort of thing as last time. You would imagine that if we have a formula for the derivative of arc cosine or cosine inverse of x, it's going to have x in the equation, not y. And we can get x in the equation. We just have to do some stuff. And it really revolves around this. So remember last time, the reason I did this one first is this part was easier. You go ahead, you get 1 over e to the y, and it's directly just x, so we could plug that in. Well, we still want to be able to plug in x, but the problem is x equals cosine of y, and we have sine of y. How can we get rid of that? Well, the Pythagorean identity is the only way to really relate cosine to sine, and it says cosine squared, I'm going to use y since we're using the angle y here, plus sine squared of y equals 1. Now, how does that help us? How is this going to help us? Well, we have what x is. It's cosine of y. What if we solve for cosine of y in this equation, then we can see there's going to be a sign in it, and we can actually replace this. Or maybe you could also do it the other way. You could solve for sine of y and go from there. So whichever way you want to do it, because my equation here has sine of y in it, and that's where I'm actually plugging it in, I'm going to solve for sine of y in this equation. We subtract cosine squared of y from each side. And just so I don't run out of room, I'll go ahead and just skip writing that visible step. But if we subtract cosine squared of y from each side, we would get sine squared of y equals 1 minus cosine squared of y. And then we do the square root. And when we do the square root, we know we get a plus or minus. We get sine of y, because that's what the square root's purpose was for, equals plus or minus the square root of 1 minus cosine squared of y. Now, we'll worry about the plus and minus in just a second, but what I want to point out here is that because cosine of y, which right here is x, if you plug this in, we get sine of y equals plus or minus the square root of 1 minus x squared. And that's exactly what's here. We have sine of y, so this is going to plug in. But before we do that, we have to make a choice. Are we supposed to use plus or minus? The reason we have to make a choice is if we don't choose, then we kind of run into the problem we had before when I talked about the circle. We'd have a plus or minus, and that would give us two formulas. But the thing you should know about the inverse trig functions is that they are functions, which means they automatically pass the vertical line test. So you should only have one choice. Is it the plus or the minus? Well, the choice we make actually, there's a few ways to do it, but the easiest way to explain it is from the graph of what arc cosine of x looks like. Because the derivative of arc cosine, it's actually always either positive or negative, but that we can only tell from the graph. So let me go ahead and grab it. I already went ahead and graphed it, and remember that when you graph trig functions, inverse trig functions, you're automatically in radians, and that's what we want to be in anyway. But if you are using Desmos, you hit the graph settings, it'll highlight radians automatically. But the thing I want you to notice here is, yes, this is the entire graph of arc cosine of x. Its domain is from -1, x is -1 to x is 1, and its range, the y values, is from, well, it's up to pi, and then the lowest is 0, so 0 to pi. But you should remember that 0 to pi are the quadrant 1 and 2 angles. The domain has to deal with the fact that cosine only comes out with values between -1 and 1. But for the main point here is that our graph is decreasing, which means the derivative is negative. The derivative is always negative. So what I can do is, if I go ahead and just plug it in with the plus or minus, so I'm going to go ahead and take my dy over dx formula. I have -1 on the top, so that's going to be important. Don't forget that. Plus or minus the square root, what sine y is, 1 minus x squared. Well, if the derivative is always negative, and remember this is already the derivative formula, only one of these makes sense to choose the plus or the minus. And the reason is because when you do a square root, you have to get out a positive number. You can't do the square root of anything and get out a negative number. It is impossible. So you always get a positive number, which means this part, the square root, is always positive, and our numerator is -1, so it's always negative. If we do a negative divided by a positive number, so -1 divided by 4, it's already negative. That means we have to choose the plus here, because if we chose the minus, we would have a negative over a negative, which is positive. Yes, some high level stuff here, a lot of thinking. This one's much harder to do from scratch than the natural log, but I just wanted to show you why it's also positive, and there's not really a plus or minus there in the formula. We choose the plus, we get -1 over plus, which we don't normally write a plus, so I'm not going to write it. And then we have 1 minus the square root of x squared. And this is the derivative of arc cosine, or cosine inverse of x. Now what I want to go ahead and do is write down all 6 inverse trig function formulas below just to finish up this video. I know it's already kind of long, but after this point, you'll have all but 2 derivative rules that we really are going to have for the entirety. So let me go ahead and now write down all of them. All right, I'll go ahead and just usually the order we write trig functions, for some reason when we say them as sine, cosine, then tangent. So I'm going to do those 3 first. Our function y, and then what is dy over dx, the derivative, or y prime. Well, if we have y equals arc sine of x, this actually looks exactly like this. The only difference is going to be that negative sign. You get 1 over the square root of 1 minus x squared. And that's going to boil down to, if you graphed y equals arc sine of x, it's actually always increasing. So that's why it doesn't have a negative there. Then arc cosine, the one we just did, so we know this one, it's the same thing but negative. And then arctan, the derivative of arctan is 1 over 1 plus x squared. Now this is probably the most common one, is arctan, but these 3 are probably the only ones you're really going to use. I'm going to go ahead and just write down the other 3 because I do think you should see them, but we're not going to use them very often at all. So arc, I'm going to just do it in parallel. Sine goes with cosecant, so arc cosecant. And then cosine goes with secant, so arc secant. And then arc cotangent. All right, arc cosecant and arc secant are kind of funny looking. But the way they look, you get 1 over the absolute value of x times the square root of x squared minus 1. And arcsecant looks the same, sort of like how sine and cosine, arcsine and arccosine's derivatives look the same. The difference is one of them gets a negative, but it's actually the opposite one this time. So it's arc cosecant. But you can kind of remember from all the derivative rules, remember the trig, 6 trig functions, if your function has a c, starts with a c, like cosecant, cotangent, it gets a negative on its derivative. Same thing for the inverse. Arc cotangent looks exactly like arctangent, but with a negative. So it's negative 1 over 1 plus x squared. But like I said, these, if you have to do the derivative of an inverse trig function, you're going to use one of these three 99% of the time. 1% of the time you might run into one of these. It's just not that common, especially arc cosecant and arcsecant, because these are pretty messy. Dealing with an absolute value inside an equation already is kind of strange, and you can't do much with it beyond that point. All right, so definitely go ahead and write these down, record these. And in the next video, what we'll do is we'll just finish up this section by practicing implicit differentiation techniques and also using our new formulas we've got here along with the chain rule. I'll see you there.